Hi, in this video you will learn how to decrypt a Module-LWE ciphertexts. Module-LWE ciphertexts are the basis for the CHEM Kyber that has been standardized by NIST. We will be using Maple as this is a language that is being used in my class. So assume here is the question, you're given the ciphertext and the secret key, and we want to decrypt the ciphertext, okay? So here I assume you've already watched our video on decrypting LWE ciphertext, because that will definitely be helpful. And also we have separate videos of proper lectures that explain the math behind those formulas that we're about to use. So here we have a public matrix A that is in, so hang tight, ZQ mod x to the n plus 1 and all of that to the power k, okay? And of course times, so m times k, okay? All right. So what it means is our matrix A has this shape, okay? It's going to have k columns, and there's going to be m samples. All right. And then each of these elements here, okay, and there's going to be k of them on each row, is going to be a polynomial mod x to the n plus 1. So really a polynomial of degree at most n minus 1, okay? So what do we do with this? So we take our secret, okay, and assume that we want to encrypt a message, okay, that is also going to be a polynomial. So it's a polynomial mod, so mu of x mod x to the n plus 1, okay? So we want to encrypt a message, and each entry of that polynomial is 0, 1, okay? So you have 0, 1, so your message, if you wish, which is going to be m0 mn minus 1, okay? And it's going to be encoded in mu. Let me just scroll a little bit here. So it's going to be encoded in mu as m0 plus m1x plus and so on plus mn minus 1 xn minus 1, okay? So this is what your message looks like. And now we want to encrypt that, and we're going to hide it in a similar way as with the LWE ciphertext, except of course that we're sort of replacing all these integer elements by polynomials mod x to the n plus 1, okay? So remember that we have this matrix A, okay? And then that matrix A, we're going to perform this following operation. We're going to have A times S, okay? Where S is our secret, so it's going to be a matrix. As you see here, we have k equals 2, so I'm giving like a pretty simple example. So k equals 2. And then we take our message, okay, which we multiply. So maybe it's probably easier to see by having the multiplication, the scale multiplication on the left. So q over 2, the rounding of q over 2 times my message plus an error, okay? And that's going to be the second component of my ciphertext. Now, how do we do this as a public key cryptosystem? So because we don't have S as the encryptor, right? So the person who encrypts does not have access to S. So to produce a ciphertext of this form here, so what do I need to do? I need to first grab, so the public key here is going to be A times S. I'm going to actually just erase this. So A times S plus an error, okay? So this is going to be public, okay? And then of course, A. Okay, these two things are going to be public. So I'm going to draw a vector x that encodes a choice of my columns. Okay, so I'm going to say to draw a new instance of the LWE problem. I'm going to select rows of A and I'm going to add them up together. And so X is going to be a left multiplication, so an addition, a linear combination of the rows that has 0 and 1s in its coefficients. And if I do X times A, okay, and I call that AX, then that gives me simply an addition of the rows of A that are encoded in the coefficients of X. And then I can take, so if I take B, okay, so if this is B, usually it's called B in the sort of general LWE framework. And then if I do X times B, okay, and I can call that, of course, I can call that BX, but you'll see we're gonna add to it. We're gonna add the message. So when I called what I called BX up there incorporates the message. But X times B, what does it look like? It's gonna be X by linearity, X times A times S plus E. Plus X times E. Okay. So this is supposed to be small. If the error was small, then hopefully X times E is still going to be small. And this is just AX times S. All right. So if I do, to encrypt, if I do X times B plus Q over 2 times my message, whoops, that's a terrible mu. So plus Q over 2 times my message, which is something that I can absolutely do without the key, okay? So without the secret key, I can say grab B, grab X times B plus the key, and that looks like this. Once you've expanded, you have AX times S plus, let's call that E sub X, the error, plus Q over 2 times the message, okay? And that is the ciphertext of the form that I wanted. Like, you remember what I didn't write it down. So here is the ciphertext that I want. This kind of ciphertext resembles very closely an LWE ciphertext, of course. The difference being that the nature of these elements, okay? So S here is a matrix with polynomial elements. And then in the end, this is a polynomial instead of being an integer mod q, okay? So now here comes the real interesting part. How do I decrypt this, okay? I felt like I had to explain where it came from, but really what's interesting to solve this particular question is, okay, where do I decrypt this? So this is going to be my bx, okay? So my second coordinate of my ciphertext. So here I give you an AX and a BX. Now, first, with the knowledge of the secret, I'm going to be able to reproduce this term here, okay? So this term here, which is the term with the secret, so AX times S, that given AS and X, obviously I can calculate, okay? So I can first, whoops, so I first calculate, oh, I'm having a technical issue here. So I first calculate AX times S, all right? From AX and S. And then I perform the operation BX minus AX times S, which gives me what? Which gives me Q over 2 times my message plus an error, okay, which I'm not able to necessarily retrieve, but I know that the error will have coefficients by design. The coefficients of the error, okay, so this is going to be an error which is a polynomial, okay, so let's call it, let's say E0 plus E1x plus dun 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 plus n minus 1 xn minus 1. All right. And each of these coefficients will be bounded by q over 2. Okay, so E0, for example, so I mean each EI will be bounded by q over 4. Okay? And what that means is that when you look at this polynomial here, it's going to be a polynomial whose entries are going to be approximations of zeros and ones. And then if the entry is close to zero, I mean, is within the distance q over 4 to 0, then we will declare that the corresponding entry of the polynomial mu was a 0. And if the entry was close to 1 plus or minus q over 4, then we'll say that the entry of mu was 1, right? And so it's all centered in q over 2, all right? So q over 2, if it's a 1, that's close to q over 2. If it's a 0, it's close to 0, okay? So we're going to go back to that right at the end, but first let's just try with that example here and see what happens. Now, I have already typed a bunch of Maple code that will help us get to there quickly. So if you're following with Maple, you may have to pause here to write down a few things that are important for all of this to work. So let's go step by step. First, I need to load a linear algebra package. So really do not pay attention to this. Okay, it's just giving you see determinants, matrices, and all that stuff. Okay, now here it gets a tricky part. Because we're working on matrices with entries in a particular ring, you know, like modular polynomials, I mean polynomials modulo x to the n plus 1, Maple has to be told what to do with that, okay? So it can do linear algebra with that ring, but we need to first load what's called a linear algebra generic, okay? And then we have to design what it means, I mean, define what it means to add and multiply, and what's the unity, and what's the division of polynomials mod x to the n plus 1. So here, notice that q equals 11, n equals 3, and that's because that is the parameters that we're dealing with, okay? And also, well, I don't need to write it down here, but k in this case, of course, equals 2. You see, it's the size of S and the number of columns of AX, okay? Now, so to just, copy those lines, okay? So I'm going to show it real quick. You just need to copy those lines from here, and you see all these blocks here. And this big block essentially tells Maple what it means now to deal with matrices with entries being polynomials mod x to the n plus 1 mod q. Okay, so x to the n being 3 and mod q where q equals 11. Okay, so that's a little bit cumbersome, but copy those and everything will be right. Okay, so I'm going to just press enter here. All right, and that has just defined. So first use the linear algebra generic, and then define all these procedures of adding and multiplying and dividing of polynomial mod x to the n plus 1 mod q, okay? Now I have my matrix AX, C, and so AX, and then BX, and then S here, okay? And now I'm going to multiply AX by X. So notice the syntax that I'm using, and that's specific to Maple with different computer algebra packages. The multiplication of AX by S might be different. You have to use the matrix multiply, and between brackets ZQM, where ZQM was the name that I gave to multiplication to arithmetic of polynomials mod x to the n plus 1 mod q. Okay, I called it ZQM. You can call it whatever you want, but then you have to be consistent here when you ask for a matrix multiply in that ring. Okay, so boom, matrix multiply. So here's what happens. I multiply AX by S, and then I took my BX, right, which is given by, 10x, there's just a one coefficient, 10x, 2 plus x plus 9, and I cancel that contribution in AX S, and here is what I get, okay? And this is where, so 5x squared plus x plus 7, and then we're going to go back to the drawing board to analyze that. So remember 5x squared plus x plus 7, okay? So we had here, so whoops. So we had here 5x squared, oh, I already forgot, 5x squared plus x plus 7. Okay, so 5x squared plus x plus 7. And now we're trying to do the rounding of all that, knowing that a coefficient close to q over 2, so remember q here is 11, okay? So a rounding of q over 2. So a coefficient close to 5 is going to be considered a 1, and a coefficient close to 0 is going to be considered so within the factor 2, okay? So plus or minus, so 0 plus or minus 2 is going to be considered a 0, and then 5 plus or minus 2 is going to be considered a 1. So the 5 here goes to a 1, then 1x, so this is 0 plus or minus 2, right? So that goes to 0. And then 7, this is 5 plus or minus 2, so it goes to a 1. So really, after the rounding, what I get is x squared plus 1 is my message, okay? There is, again, something that I said in the video on how to decrypt an LWE ciphertext that you need to be careful about is if you have a negative, okay? If you mod everything by, so here 11, what's gonna happen, of course, is that a given coefficient, okay, so if you have your 0 here, and then your 5, okay, and then things can go up to 10, okay, when they're working mod 11. And then what happens here is that, so from say 3, so 3, 4, 5, okay, I declare that to be a 1, and then 5, 6, 7, okay, I declare also that to be a 1. But then if you have something close to 0 but in a negative, remember that if you mod by 11, you're gonna have this, so this part, okay, the things that are 0, so minus 1 or minus 2, these will go here, okay? So really, you have to be careful. This is, this is a 1, okay? And if you have a 0, let me just change the color here. If you have a 0, then you have, so this is a 0, okay? But also, when you mod the negative value, the small negative values by 11, then you will wind up in this region, okay? So that's the only subtlety. I said it already in a similar video on how to decrypt LWE ciphertexts. But it didn't really occur to us. I mean, it didn't really happen to us here because we had a 5 and a 1 and a 7. So, but bear in mind that those little errors in the LW and Module-LWE ciphertext, they can be chosen with negative coefficients. That's really the only little trick here. All right, so now you know how to decrypt a Module-LWE ciphertext using Maple. Thank you very much for watching.